One of the things we're often interested in science is being able to express the relationship between the amount of solute and solvent. We call this relationship my concentration, where my concentration is equal to my amount of solute in a solution divided by the amount of solvent present in that solution. Now, when we're talking about concentration or solutions, we can say that a solution is concentrated if it has lots of solute in a given amount of solvent. And we can say that it's dilute if there are only a few solute particles in my solvent. Now, this is a description of the amount of solute, but the mathematical relationship between them is called the concentration. Now, we have different ways of expressing this that we're going to look at. First one is called our percent composition. Then we have our parts per million, parts per billion, or parts per trillion. For extremely low concentrations, we're going to look at parts per million. And then finally, for chemistry, the one that we're really interested in, which is our molar concentration. Now, for a percent composition, we can express them as a ratio. And there are different types, and these are often used in the industry. So we have our percent volume by volume, where both my solute and solvent are liquids, and when I combine them, it's a relationship between the volume of each of them. And we find this often in alcohol, where if we have a 10% volume per volume, 10% alcohol to 100% of the drink. And we have our percent weight per volume, and we also can have percent weight per weight. So if I had a solution of alcohol that's 25.6% alcohol, then there's 25.6 milliliters of alcohol dissolved in 100 milliliters of water. Likewise, if I have a sugar solution that's 12.5% weight per volume, then it's 12.5 grams of sugar dissolved in 100 milliliters of water. So let's take a look at a couple of examples where we would be asked to calculate this. So here we're told that we dissolve a certain amount of sodium chloride in a certain amount of water. Now, just like we always do, we always write down our givens. Okay? And one of the key things is to remember is that your masses are in grams, your volumes are in milliliters. So now that I have my values written down and I have them in the correct units, I can write down my equation. For my percent weight per volume, it's the mass over the volume. So I can substitute in my values and solve. Likewise, if I'm asked for my percent weight per weight, because the density of water is 1 gram per milliliter, 2,000 milliliters is 2,000 grams. And so then I can write down my equation, substitute in my values, and solve. So percent relationships for my solute and solvent are good when there's large amounts of solute in a relatively small amount of solvent. And they're often used in industry. But when I have a very low amount of solute in a given amount of solvent, we use our parts per million and sometimes even parts per trillion or parts per trillion. So parts per million is denoted as ppm, and these are very low concentrations. In fact, 1 part per million means that there's 1 gram in 10 to the 6 milliliters. Now that relationship is a little hard to visualize. The form of the relationship that we often will use is 1 milligram per liter. And so if I have my amount of solute in grams and I have my volume of solvent in liters, then I could substitute my milligrams per liter for parts per million. So here we have some oxygen dissolved in water, and we record our mass of oxygen that's dissolved, and my mass is in milligrams. We were given our volume in milliliters, but we can convert that to liters. So now that I have my mass in milligrams and my volume in liters, Once I'm done, then I can substitute the milligrams per liter for parts per million. So my concentration of my oxygen is the mass divided by the volume. So we substitute in our values, and we end up with 8.8 milligrams per liter. And so now, since 1 milligram per liter is 1 parts per million, I can just substitute the unit. So it's key that you remember that relationship, that 1 milligram per liter is equal to 1 parts per million. Now, both of those are interesting ways of expressing concentration, but the method that we're going to mainly use in class is molar concentration, because our reactions take place between moles, or particles, and moles being groups of particles. So therefore, we have to have a way of knowing how many particles are in a given amount of solution when we do our reactions. And so this is why we're going to use molar concentration, where my concentration is equal to my moles divided by my volume. Now, because we know moles is mass divided by molar mass, I can also say that my molar concentration is equal to my mass divided by my molar mass times my volume. So let's take a look at an example. So we're going to determine the concentration of each of these, because each of these point out different things. So for A, we're given my amount of solute in moles already, and we're given our amount of solvent in liters. So all we have to do is we write down our givens, write down our equation, and then just easily substitute these values in and solve. So we get 2.29 moles per liter. So that was a relatively straightforward one. Let's take a look at another example. In this case, we're asked for our volume, and we're told our concentration, and we're told the mass of our solute. So again, we write down our given values. Now you'll notice here that rather than using C for concentration, I've written the chemical, and I've put it in square brackets. And so this is a way that we represent concentration often in equations. So this square brackets with MgCl2 in it would represent my concentration of my magnesium chloride. Okay, we know we can calculate our molar mass. We know our equation, so my concentration is equal to my mass divided by my molar mass times my volume. I'm going to manipulate my equation to isolate for volume. I can substitute in my values and then solve. So it would take 1.3 liters to have a mass of 6.81 grams. Okay, and then for our final example, we're told our mass and we know our volume. So this is relatively straightforward, hopefully at this point. We write down our mass. We know we need our molar mass. We have our volume. We're solving for our concentration. So we substitute our values in. And you'll notice generically here I just said concentration is C. But once I'm referring to the concentration of a particular thing, I'll tend to put it in square brackets. Okay, so my mass divided by my molar mass divided by my volume. And we get our concentration of our solution.